So this must be the minimum energy. What does it contain? Hard to interpret this, but let's interpret this. An electron 2 is sitting on chi j. I am integrating for an electron sitting in chi I, one electron sitting in chi I. The electron 2 is sitting in chi j and giving an average interaction, one particle interaction. This is the density, remember, chi j star chi j. It is just giving an average one particle interaction on an electron sitting with chi I tilde. This is the classical electrostatic interpretation for the Coulomb term, that I have an electron 1 which is sitting on chi I tilde. There are another electron sitting in chi j tilde. It is moving all across. I mean, it's a classical interpretation. So electrons are not moving; it's a density. So the entire density chi j star to chi j 2 is integrated between d tau 2. So integration essentially means it moves all across, and what the electron 1 sees due to that. So this is a classical electrostatic force that the electron 1 sees due to the movement of 2. Of course, you can say, what about 3, what about 4? I don't need to do. That has been achieved by the sum. Again, I repeat. So everything can be 2. So I just rename these electrons. They are in different spin orbital. Is it clear? So it is basically a classical electrostatic interaction that the electron 1 sees due to electron 2, and then one particle part has been extracted by averaging, because I need a one particle part. That has been extracted by d tau 2. Essentially, that means the 1 and 2 are dynamic, but 1 sees a total average effect when 2 makes a complete movement. Assume they are classical particles, then 2 could have made a one full circle over electron 1. Then on that circle, after that, what is the potential that the electron 1 sees due to electron 2 is what is captured here in this square bracket. Okay, so that's I am now going into the interpretative part of the Hartree form, which I will write maybe in the next class, but let me first state. I will write that more clearly, the interpretation. But now I have another part, exchange part, which I am not able to interpret, because now this is not a density. So electron 1 was sitting in chi I 1. Now this electron 1 is sitting in chi j 1. So this was chi I 1, this was chi j 2. Now they have flipped. It has gone to chi j 1, and the d tau 2 interpretation is also very funny. It is on 2 on chi I, and this is chi j star. So I don't know what interpretation I will give, but that's the nature of the exchange. That's the nature of the antisymmetry. That no electrons are not classical. So that is something that I have learned from the beginning when I wrote the energy also. I could not give an exchange classical interpretation to exchange interaction. I am not able to give a classical interpretation to this operator, whatever this operator is. Okay? And then of course I have a further problem, that this is not in the eigenvalue equation structure yet, because it is not a number times chi I tilde 1. If it was a diagonal, it would have been number times chi I tilde 1. I hope all is clear, right? If this was diagonal, this j is equal to I, so it would have become number times chi I tilde 1. But let's not worry about it right now. We will see how to do that. So that would be actually a canonical Hartree formulation. When lambda becomes diagonal, we will actually get, now I can tell you what is canonical. That will actually lead to canonical Hartree formulation. How to achieve this? I can't make an approximation, because if I approximate this, then that is wrong, because then you are saying canonical is only an approximation. That's not true. We will achieve this by exact means. So that there is a lot more to it, but right now we are stuck with the non-canonical. But our problem is that I can't still, even if it was canonical, I can't make it into an eigenvalue equation form because of this exchange part. So assuming that this is a diagonal, I can't still write it as an eigenvalue equation form because of this guy. See, this is already eigenvalue, something times chi I tilde 1, something times chi I tilde 1, something times chi I tilde 1. I mean, I would only assume they're diagonal, but what about this part? And that was his question. And so the exchange part we always have a problem. However, I will quickly show you that formally, mathematically, I can derive an operator by making this look like a chi tilde 1, because that is what we want. The 1 should be on chi tilde, right, on the right hand side. So let me analyze this term. So let me come back only to the exchange term of this, which is chi j star 2 1 by R12, what is it, chi I 2 d tau 2 chi j 1, right? No interpretation, because chi j star 2 chi I 2 is no exchange. It's not a density. This is j, this is I. Sum over j, of course. Now, what I will now do is strictly mathematical, and you may even consider that as a cheating, but it's mathematical. What I will do, I will write this as sum over j, chi j star 2, 1 by R12. I will introduce between these an operator which you are already aware of, permutation operator, P12. Permutation operator interchanges 1 and 2. So, I will write this P12, and then of course, they have to be interchanged. So, this guy will now become chi j 2 and then d tau 2, and this guy will go out as chi I 1. Perfect, I have no problem. You may only say, what would it do permutation of that? That's the later part. I want to write a formally eigenvalue equation, right? So, what I did was simply nice mathematics. I just brought this inside P12 between 1 by R12 and this. And moment I do this P12, these two will be equal only if I have interchanged 1 and 2 on the right, because P12 acts only on the right. We have already done what is P12, permutation operator, right? So, I am going to bring the permutation operator here and then write this term very easily. So, now this term would be written as P12 chi j 2 d tau 2, so tildes, whatever, chi I 1. Beautiful, right? Now we have something acting on chi I tilde 1 equal to, assume this is diagonal, we will talk about that, number times chi I 1, right? Now the question is, what is this? This we know, it's electrostatic interaction of 1 by R12. This is also an electrostatic interaction, you can assume, of 1 by R12 P12. That's my operator. Who cares? It is just that the operator is not a classical operator. So, during that process of the Hamiltonian, I am saying that Hamiltonian has a 1 by R12 for the classical Coulomb part. For the exchange part, it is actually 1 by R12 P12. That is all I am saying, for only if you want to interpret. But that interpretation is up to you, physical interpretation. But if I write it like this, then I can immediately write the Hartree-Fock equation in a nicer form. Okay, it's all about writing nicer form. All are right. The original one was right. So now what I do, I define an operator called F. Now this is something that you know, Fock operator. This operator is called Fock operator, F of 1, which is just the operator, H of 1. So I am not going to write the chi I tilde 1. They will be all out. Plus sum over j, I am only writing the operator part. Chi j star 2, of course, this has to be integrated. 1 by R12, 1 minus P12, chi j tilde 2. I am going to do even more simplification. I don't want to write the Coulomb and the exchange. Right? I just achieve this. 1 by R12, 1 minus P12. 1 gives me the Coulomb, P12 gives me the exchange. No problem. So, eventually, I am doing a classical interpretation of an operator called 1 by R12 to 1 minus P12. As if electron 2 sitting in chi j thing and they are interacting via this potential. The potential I have only changed from 1 by R12, 2 particle potential has become 1 by, beautiful. If this is what it is, then all my Hartree-Fock equation is just f of R1 chi I tilde 1 equal to sum over j lambda ij chi j tilde 1. That's my general Hartree-Fock equation. Is it okay? Now I have very simplified. I think I have to go through once more. Necessarily I will go through once more tomorrow, the entire algebra, because this is the part which is never done. in the classes, because they just come to that equation finally. Because nobody wants to derive this dirty thing. So I have taken the risk of deriving. Risk, trouble, no. Because the derivation I can do while sleeping also. So there is no trouble for me. The risk, because it may put you off. So I have only taken the risk, no trouble for me, don't worry. I can keep on deriving every time you want. So eventually I get a very nice Hartree-Fock equation. That is called the non-canonical Hartree-Fock equation, where f of 1 is defined as this. So I have written everything now. These 2 lines write my Hartree-Fock equation. If provided I can make lambda diagonal, it will be a canonical Hartree-Fock equation. I will see how to do that. That is a final part in the jigsaw puzzle that I will leave, but both are right. We will see formally exactly you can make it canonical Hartree-Fock equation. So both are okay. But this is a general non-canonical form which is yet not in the eigenvalue equation structure, simply because this is not diagonal. Otherwise it is equal to something, and you know that diagonal values, if I can make it diagonal, those are my orbital energies. All of you already know f chi equal to epsilon chi, right? Everything is known to you, all of you. So I'm going to come to that a little bit later, but that's the final piece which I leave it as it is. And before I do that, I have a lot of other observations I have to make. So this then becomes an Hartree-Fock operator. So does it answer your question? How can I do it? Mathematics allows me. No, not the physics, but this was a clever trick. If you want to write it in this form. But okay, eventually when you integrate, it will become complicated. Yeah, the exchange part will spread it. So that's the problem of the exchange part. That, see, physically I am not saying that problem is simplified, but see, because the P12 is a non-local operator. Note, what is the problem? Why it is spreading, as you said, for exchange? Because of P12. So if you look at this operator, this is a non-local operator in a very way of saying. And this is where later on you will see the problem of density functional theory comes in. Because this is density, no question. But unfortunately, here it's a non-local. So when people want to write density functional theory with local exchange, it's an approximation. That's the way LDA is an approximation. And this is the biggest problem in density functional theory. How can I do it without actually doing like Hartree-Fock? But Hartree-Fock, there is no problem. We can do it, we have no problem. Because it's only a question of an iterative solution. Well, I will come to the solutions and all that later, but I think first you should digest the equation. So remember, I had a Lagrangian first when I started. It's a long process. I again repeat what we did, and you have to go. No, okay. So you had a Lagrangian, and then we said that if I make these changes on chi till, I did not bother about change in the with respect to lambda, because anyway that will give you the equation that was already known. If you change chi first order change in Lagrangian should be 0. The Lagrangian explicitly included this. So then I made a first order change. So that was delta chi L 1. Then they had delta L equal to 0. Then I found that there are lots of terms. Of course, the complex conjugate part I had already knocked out. Then within the Coulomb and exchange, I found that both the terms are identical. So the half was knocked out. There's only one Coulomb and one exchange with delta chi 1 on the left. Delta chi 1 star 1 left. So since I've integrated the whole thing to be 0, the integrand was equal to 0. Because for arbitrary delta chi 1, if I do, this is called integrand. What is being differentiated, what is being integrated, that integrand was equal to 0, and that was my equation. And on this side, the similar thing came. This was my integrand. Then I wanted to write down the integrand, that g of 1, which basically turns out to be of this form, where everything is now a function of 1, but where explicitly chi tilde 1 appears. So if I now say that integrand has an operator acting on chi tilde 1. What was my g of 1? The g of 1 is nothing but this operator. You remember the g of 1 I wrote, that was integrand. It is operator f of I chi tilde 1 for each I. So g of 1 will keep changing. Okay, so you remember my final equation was delta chi star 1 g of 1, right, minus sum over j lambda ij delta chi star 1 chi j 1, right? This is my original form, beta 1. Now I am saying this integrand is nothing but an operator times chi tilde 1. where the operator is has the H plus the exchange and the Coulomb term, plus the exchange and the Coulomb term, okay, of the operator, which actually is contained in the G, which is basically given here. The interpretation of the exchange is the difficult part. We still don't know how to do it, and how to actually mathematically implement, that is very easy. That I will show next time. But so this was basically the equation that I said, and this particular operator is called the Fock operator. One important thing, however, to note is that this Fock operator is not defined offline. The Fock operator is not defined offline, because to define Fock operator, I need the chi-j. This is a very important part to note. Even if this was an eigenvalue equation, normally what you will do? I have an operator, just diagonalize. I will get chi-i tilde 1. But here you can't get, because your operator is not defined. The definition of operator itself depends on this, which is supposed to be the output of this equation. So you can see that even the Hartree-Fock, which looks like now an operator eigenvalue equation, assuming this is diagonal, canonical form, it's still not easy to do because I don't have the operator form. So even the canonical Hartree-Fock equation is really not an eigenvalue equation. Many times this is called the pseudo eigenvalue equation. And we will discuss in detail how do you solve it after I first get the canonical Hartree-Fock equation. So there are two important pieces that are still left. How do I canonicalize? I am now assumed it is canonicalized. And then how do I actually solve it, because f depends on the chi's. So the important point here is that because f depends on chi's, one obvious way to solve is an iterative solution. That is, assume some chi's, define the Fock operator, then solve the eigenvalue equation, assume it is canonical, get the new set of chi's, again redefine Fock operator, and continue to do till it converges. All mathematics, you know how to do that, iterative solution. When it converges, what it means is that the field, what is the field? The field is of chi-j's. Chi-j is the field of the electron 2. That field which is defining the Fock operator is the same which comes out after solution of the Fock operator, because after solution I am getting the spin orbitals. The field which defines the input comes as the same field as output. So my field is chi-i. So that defines my Fock operator, that's a box. And then I solve some HF equation, right? HF equation, I get the same chi-i. If that happens, that is what happens at the convergence point. Normally no. When that happens, I am very happy because I have actually solved the equation. And this is the reason it says that the field which defines the Fock operator is the same field that comes out of the Fock operator, and we call it self-consistent field. Or symbol SCF. You might have heard the word SCF many times. SCF has been synonymously used as Hartree-Fock actually. But let me again repeat, Hartree-Fock is the method. SCF is only a procedure to solve Hartree-Fock. Many people forget. Because somebody can come up with another way to solve this equation. Okay. SCF is a procedure where I solve the Hartree-Fock equation iteratively till the field which defines the Fock operator becomes the output of the Fock operator. So that is the reason many times Hartree-Fock is called self-consistent field. But remember, SCF is a procedure. Many people confuse actually, because we normally now say SCF method. We even forget that the Hartree and Fock did it. But Hartree and Fock actually derived the method. SCF is merely a procedure. I can use some other procedure. Of course, many people write HF SCF method just to make sure that they are right. Hartree-Fock and then self-consistent, right? You have seen all kinds of nomenclature in the programs and textbooks. So I'm just trying to make sure that you understand that this is Hartree-Fock. The procedure to solve this equation is SCF. Even the canonical part cannot be solved easily because of the fact of dependence of F on the chi, and that is where SCF comes. I will again repeat these points, of course, and write down tomorrow 1, 2, 3 after everything is done. But one very important piece is canonical lines that I have not touched yet. Okay, so that will take little bit more time. Once I do that, this is a small thing, but is very important. Okay, because we usually use. However, I don't have to teach you canonical Hartree-Fock equation because this is still right. Okay, everything I will show you. Everything is same, except the orbitals. Orbitals will change, energy will be same. But unless you have a canonical Hartree-Fock equation, you will have a problem in chemistry because you don't know what is orbital energy. Right? Orbital energies are eigenvalues of the Fock operator. Here there is no eigenvalues. So you can't do ionization potential, you can't do electron affinity, all that HOMO, LUMO that you have seen, I can't do it. The only thing that I have achieved is the Hartree-Fock energy. Hartree-Fock energy will remain the same, the final energy. Okay? So I have to bring in canonical equation. Okay, I can assume that you can do it and write it, but that's not a good way of doing it. I will show how to do it, bring it formally, and then you will have all those interpretations. HOMO energy, LUMO energy, HOMO minus 1, LUMO plus 1, all kinds of things that you people talk, they will all come after that. That interpretation of orbital energy, Koopman's approximation will not come unless I go to canonical equation. So this is a very important piece. Just for the time being, to make you understand, I have assumed it is canonical. But this is a very important point. Even if it is so, the Fock operator depends on the spin orbital. So it has to be solved by an SCF procedure, self-consistent field procedure. So if I ask you to write what is self-consistent field, you should be able to write properly. Okay.